Hi there, this video is to talk about how to do equilibrium expressions and the math behind it. So let's start with this first one, and I've got a total of 4 to do. We'll see how we do. After a mixture of hydrogen and nitrogen gases in a reaction vessel is allowed to attain equilibrium. When I see that word equilibrium, that's saying to me a certain type of math. And it says later on, it is found to contain 7.38, 2.46, and 1.166 NH3. From this data, calculate the equilibrium constant, Kp. So I'm going to do math part. I know I have to find Kp, so the first thing I'm going to do is write the Kp expression. Now that's always going to be equal to the products over the reactants. We've got to be very careful though. That P means we've got pressures. Sometimes they leave off the P and it's just the K, but we have to realize with the units, ATM, that's units of pressure. So when I write this, I have to write it as the partial pressure of my products go on top, NH3. The 2 is what it's squared by. You can put it in parentheses, but you cannot put it in brackets. So if you do it like this, that is automatically wrong because those brackets mean concentration, so be careful with that part. I would suggest just leaving it as the P with the squared. Divided by my reactants, partial pressure of nitrogen, it has a coefficient of 1, times the partial pressure of H2, and that has a coefficient of 3, so I put it to the third power. And now that I have that, I just want to find the Kp expression, which means I want to plug and chug in the numbers that they gave me. So they gave me that 7.38 is the partial pressure of hydrogen at equilibrium. So 7.38 goes here. They tell me 2.46 is nitrogen. And NH3 is at 0.166. So I'm going to simplify it over here. 0.166 squared. Don't lose that spot. 2.46 times your 7.38 to the third. And here I'm just going to push all the buttons in my calculator to get the answer. My calculator sounds like this. Boop, 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 boop. You're welcome. I get 2.79 times 10 to the negative 5. Now when we're dealing with these numbers, I do want to think about sig figs. All the numbers are 3 sig figs, so I put 3 sig figs in my answers. The final thing is there are no units ever on Kp. Any of your K expressions do not include units. It's just a unitless number. And remember, the reason we have this number is to tell us if it's reactants or products favored. This is a very small number, so this is reactants favored. Meaning at equilibrium, we'll have more reactants than we do of the products. Alright, try number 2. This one gets a little bit different. A closed system initially. When I hear the word initially, I know that it's going to be a little bit trickier, this math. It tells me at first I've got this stuff, at 448 degrees Celsius. And it's allowed to reach equilibrium. And then it comes to equilibrium. There are 2 steps to this problem, if I read carefully. Initially, and then at equilibrium. Analysis of the equilibrium tells me that I have an HI of this much. So I have to calculate the Kc at this temperature. Okay, so if I need to calculate the Kc, the first thing I should do is write the equilibrium expression. Now remember, K is normally how they'll write it, but they could write it with a C, and the C just means you're going to do it by concentrations. That's kind of important here because I've got gases, so I could do it in partial pressures, but I would notice that the units are in molarity, so I know that it's going to be in the concentration instead. So I'm going to write the equilibrium expression, where I have products. In these brackets, remember the brackets mean molarity, squared, divided by my reactants. H2 and I2 are both 1-to-1 coefficients, so I just have H2 times I2. There's a multiplication sign there. You can have it or not. So now the fact that it says initially and containing and all that kind of stuff, I know I've got to do things a little bit different here. I want to set up myself an ICE table. And in ICE table, I've got the reactants making the products. And what the ICE table stands for is initial, change, and equilibrium. So I'm going to be putting in the numbers that I have at each of those spots. Because remember it says initially I've got this much H2. 1.000, that's a lot of sig figs. It's 10 to the negative 3. I'm going to fix this a little bit. And then my initial of I2 is 2. And initially, I don't have any of my 2HI. It's put in as a closed system, So what that means is they added in this much H2 and they added in that much I2, and the reaction hasn't run at all. So initially I have none of the HI. And then change happens. In other words, I start to lose some H2, maybe we'll call it an X amount, and I start to lose some I2. For every one H2 I lose, I'll lose one I2. And I start to gain HI. Now it's not just X amount of HI, see that 2 there. For every one of the reactants I lose, I gain 2 products, so I'd have to call it 2X. So over time, I've lost X amount of my reactants, and I've gained 2X of my products. So then, if I'm going to take a look at what equilibrium looks like, it's going to be these two added up. So it'll be that 1.000 times 10 to the negative 3 minus X is my H2. 2 minus X. And then this part right here will be 2X. I have added 0 plus 2X to get 2X. Okay, they did give me some interesting information that kind of helps me out a little bit. They did tell me that at equilibrium, my HI is equal to that number. So they actually told me that this right here is 1.87 times 10 to the negative 3. Well, that's useful, because if I need to find Kc, I need to know all the values that are in this expression. So now that I know 2x is equal to that number, I can actually solve for x. So I'm going to say 2x is equal to 1.87 times 10 to the negative 3. That way, x is equal to 0.000935. And that'll help me solve for these values. So that I can actually put them into the expression. So I'm going to take this down this way. And I'm going to be plugging in the numbers that I know. My product, I know, is 2x, which is that guy, 1.87 times 10 to the negative 3. Now be careful, though, because don't lose this squared value. It happens so easily. That's squared. And then I just need these values in here, which is my 1 times 10 to the negative 3 minus x. And remember, I solve for x to be that 0.00935. So that gets me 6.50 times 10 to the negative 5. And 1.065 times 10 to the negative 3. If I start plugging in those numbers in my calculator, I can finally get that Kc is going to be equal to 50.5. That's a pretty big K. That tells me it's a products favored. Remember, there are no units on your K. So again, I plugged and chugged the numbers once I was able to find them using my ICE table. I knew I needed an ICE table because it said the word initially and equilibrium. That gave me a clue into that. Alright, let's take a look at number 3. It seems a lot smaller. You put in 1.2 molar acetic acid into a beaker. How much acetate ion is present at equilibrium? So I have my K, and I want to solve for one of the variables that are inside the K. So the first thing I should probably think about is, this one is going to be an ICE table situation. So I'm going to set it up right by my equation here. I'm also going to need my K expression, so I'm going to start by writing that. K is equal to products. So here I've got my acetate ion times my H3O plus, hydronium it's called, divided by acetic acid, is what that thing's called, times, well, water is a liquid, so I don't include water in the liquid. Which means in the ICE table, I'm not going to care about what values those are at all, which actually simplifies it a little bit. Now I know that the K is going to be equal to 1.8 times 10 to the negative 5. So that's cool. So now I've kind of used all my numbers that I've got. I'm going to try to fill in my ICE table now. I know it looks like I don't really have a whole lot, right? Well, something I do know is that I'm going to put in 1.2 molar. At the beginning of time, I'm going to say I've got none of these parts here. So initially, it's like you have the acid, and then equilibrium starts to change. I start to lose an X amount of this, and I start to gain an X amount of this. So that at equilibrium, I've got 1.2 minus x here, because that's how much acetic acid I had, and it started to change by losing the ions. And it created x amount over on this side, 0 plus x, 0 plus x. Now that I know that part, I can actually put it into my K expression. So down here on the bottom, it's 1.2 minus x. And on the top, it's x and x. And now that I just have one variable, I can solve it from here. So I'm going to simplify it down. On top, I've got x squared divided by 1.2 minus x. I get 1.8, 10 to the negative 5. Now, if you kind of look at where we're headed down here, if you start simplifying this and solve for x, you're going to see we're going to reach the quadratic equation. That squared part should kind of hint you into that. Quadratic equation is something chemists, we could solve that for x and actually know what it is for real, but chemists are kind of lazy and they're not big fans of that. So we always try to find a way around it. And in the AP Chem world, you can always find a way around the quadratic equation. And here's how we do it. We're going to assume that x is much, much smaller than 1.2. And if you think about it, we've got a K expression right here that's pretty small. So when we look at our ICE table, we're saying we're starting with 1.2, and some of it is moving to create products. But since the K expression is a small number, we can assume that this x value is actually pretty small. Compared to 1.2, sig fig wise, it's extremely small. So we're going to kind of just say it doesn't actually matter. So we'll say that 1.2 minus x is really just 1.2. It's okay to do that if you think about sig figs. Remember in subtraction rules, it's something like if you do 1.2 minus 0.000011, you really will come out with 1.2 again because there's no decimal places after that 1.2. That sig fig rules say it's going to be the same number as before. That's basically what I'm assuming here. It's also like if you're on a diet and you have to pick out 2 cookies, like one cookie has 5 M&Ms and the other cookie has 4 M&Ms, you're not going to be like, oh, I can't pick the 5 M&M one. Because really, that last M&M doesn't matter. You do one more jumping jack, you're good to go. So it's kind of those theory. I call it the chocolate chip cookie theory. Anyway, moving on. Now I've got x squared over 1.2. Because remember, I assumed that that x won't matter. And that's going to be equal to 1.8 times 10 to the negative 5. Now that I've done that, my math becomes a lot more simple. And I can calculate for my x to be 0.0046. Now this is an x value, so it does need units. If I go back up, this is representing the concentration of my acetate ion, which is totally what I wanted. So that solves it for me. My answer is my acetate ion. And I'm going to end those problems right there. For the next tricky problem, you'll see it in a different video. If you've got your note packet, and you've already filled that out, and you're taking notes here, there's this problem right here, and if you'd like to tackle that one, you certainly can. It's listed as number 5 in your notes, and just to give you the answer for this problem, it's 2.24 times 10 to the negative 3 ATM. Why don't you give that a shot and see if you can solve for this problem? If you can, you're doing great so far.